Assalamu alaikum. So today's lecture we will primarily be going through numerical examples of columns with other types of support rather than just a pin column that are undergoing buckling. So I'll just be taking the two examples at the end of our slides and just going through them right here on the screen. But I do want to go over the lecture slides very quickly. So I've uploaded the part 2 already on Microsoft Teams. So if you haven't seen that yet, please do head over to our subject channel and see the lecture on there. Okay, so in this week's lecture, we basically analyzed actually some other columns with which can have different types of boundary conditions or different types of support. Last week we looked at the pin column. This week we jumped to first looking at our fixed free column and then also looking at our two other types of columns. So in this fixed free column, basically we have a fixed support, which means that we have boundary conditions of zero deflection and zero rotation at this fixed end. Right? So how we look at this problem is, again, we use our method of sections to find the internal bending moment find the internal bending moment in this column, and then use that internal bending moment in our moment curvature relationship, solve that differential equation to find the deflection in our beam. And once we've got the general expression for our beam, we substitute in our boundary conditions at this fixed base. And when we do that, we can basically solve for which types of loads are possible, essentially, that can lead to the buckled deformation or buckled configuration. And this time around, it turns out that our critical load actually is, the smallest critical load actually is pi squared EI divided by 4L squared. Now this is interesting because we have already done the analysis for our pin column, where we saw actually that the critical load was just pi squared EI divided by L squared. Whereas in this case, for our fixed free column, we've got a critical load which is 1/4 that for our pin column. This means basically that because of these boundary conditions of fixed free boundary conditions, our column is actually 1/4 times weaker, essentially. It can only take 1/4 the critical load that our pin column can take. So these boundary conditions lead to a weaker configuration of our column. Right. Now this leads us to define this concept of effective length, basically, where we carry on using our Euler formula, that is this one right here, pi squared EI divided by L effective squared, to define our critical load for all types of columns, except here that now we've got an effective length in the denominator. Now, this effective length basically we define for any column to be the length between 2 points of zero moment for that column. Okay, so it's the points of zero moment. And where we have zero moment, we have zero curvature, and hence these are also known as inflection points of that of the elastic curve of the beam, basically. So if we were looking at our pin column, now the points of zero moments are these pin supports, hence why the effective length here was just equal to the length of the column. Whereas if we looked at our fixed free column, this time around the point of zero moment is this free end, so we actually need to consider a mirror reflection, imagined mirror reflection of our column to get to our second point of zero moment, such that the effective length in this case turns out to then be 2L, such that when we square it in the denominator, this leads to our 4L squared in the denominator that we found, right? Whereas the nice thing about using just the effective length is that we can use the same formula so long as we know what the effective length is for either the pin or this fixed free column. Similarly, two other types of columns can also be looked at. One is our column with fixed ends on both sides, so fixed here and fixed here. Now in this case, the effective length is actually half of the total length of the column and occurs in the middle section of the column, basically. And then another column that we can look at is our fixed and pin column. And this time the effective length is approximately 0.7 times the total length of the column. And using this effective length, we can then directly calculate each of these columns' critical load using our Euler load with pi squared yikes, what that turned into EI divided by L effective squared. So as I said, this is a very important result and it's worth committing to memory even though you will be provided it. Okay, great. Now, our effective length can also be represented in terms of the total length of the column using our effective length factor, such that then our Euler load can be written not in terms of the effective length, but in terms of this effective length factor K. Okay, so nothing too special, just that we're representing the effective length in a slightly different way. And once we do that, all of our results can be summarized right here. So the pin column has an effective length just of the length of the column, so K is 1. Whereas for our fixed free column, the K is 2, such that the effective length is 2L, so that when we square the effective length, we get a 4L squared in the denominator here. For a fixed column, the effective length is 0.5 times the length of the column, so K is 0.5, and when we square that, there's actually a 4 going up right here. And similarly for our fixed pin column, the effective length is actually 0.7 times L. Okay, and then that leads to its corresponding critical load, basically. Okay, so that's basically it for the analysis part that we've done. Then I had a few examples in the lecture slides of how we actually provide extra supports to columns in order to increase their critical loads. So for example, you may have often seen very long and slender columns being braced somewhere along their lengths like so. So this is a water tower which has been braced at a few positions along its length. Now basically what this does is it provides an extra support such that it basically reduces the effective length so that it's no longer equal to this entire length of the column, right? It's not equal to that. And then it's some function of what these supports provide. So if this is a fixed support, then the effective length becomes shorter and would just then become 0.5 of this length, right? So that's why this is important. Similarly, we also have earthquake resistant beams which are used for construction. Now what these essentially consist of is an internal steel core together with an external steel tube which goes around this steel core. And the purpose of this steel tube basically is to prevent this steel core from buckling laterally in either of these directions, right? So this steel tube goes over it and provides protection against buckling for this core. So these you may see not so much in Pakistan. I haven't seen them outright. Some people who build very expensive houses themselves do use them, but abroad you can find them in I think this is a parking lot being constructed, so you can see it right here. So this yellow portion is its steel tube and then the gray one is the core right here. Okay, great. So moving forward with that, another example of real world columns being braced is for pressure vessels. So sometimes pressure vessels may undergo external pressure, and in that case that leads to compressive stresses being set up in the wall, and those compressive stresses can lead to buckling of the wall of the pressure vessel. So in order to prevent this sort of situation arising, these pressure vessels tend to have stiffeners going around them. Now they may be either internal stiffeners so that they are inside the pressure vessel, or external stiffeners which we can see outside, something like this. So these essentially prevent buckling. So if you can see, it didn't buckle from this top portion right here, but it buckled between these two stiffeners. So perhaps there was another stiffener required here to prevent this sort of buckling happening. Okay, so with that, let's move to example number 2 in the lecture slides. So basically we have a standard W150 by 24 steel column. Now again, as I've mentioned before, this is a standard column, which means that we can look up a beam chart and figure out what its moments of inertia are, where its centroid is, what its cross-sectional dimensions are basically. And it is 8 meters long and is fixed at its ends as shown. Its load carrying capacity is increased by bracing it about the YY axis, so only the YY axis, using struts that are assumed to be pin connected to its mid heights. So this in the YY axis, about the YY axis, is acting like a pin joint. And it says nothing about the X axis, so that means there is no extra support being provided about the X axis. Okay, so determine the load that it can support so that the column does not buckle, nor that the material exceeds the yield stress. Okay, and then the material properties and the geometric cross-sectional properties. Great, okay, so let's have a think about this. So we have our two axes, X and Y, okay? So we're going to analyze basically buckling occurring about either of these axes. So let's first take a look at my X-axis. Let's start with that. So I know if I'm looking at buckling about my X-axis, what I need you all to do right now then, again, buckling is a problem in bending. So if you're looking at bending, then we can use our right hand grip rule basically to figure out what that plane of the bending will be, or where that turning effect will be arising. So if I'm looking at buckling about the X axis, let me point my thumb in the direction of the X axis, let's say in this direction. Then I'll see, using my right hand grip rule, that my turning effect is something like so, right? That means that it will be buckling sort of along sort in this plane. Does that make sense? So this is the turning effect that it's producing. Let me draw out what potentially that plane it is that I'm saying. So I'm saying if I'm looking at buckling about the x-axis, that means bending about this x-axis, then the turning effect is something like so. That's the turning effect direction. Okay, so let's draw that out. Let's draw that out separately. So I'm saying that I am looking at buckling about my x-axis. So I have my x-axis, let's say, going into the page. That means basically buckling in this plane which contains the y-axis. Okay, so buckling about the x-axis, and in this plane I know that I have no extra supports, and all that I have is the fixed two ends. That means fixed end right here and fixed end at the base. Okay, so these two boundary conditions. Now, what would the buckled shape look like for a fixed deformation? That we know takes this sort of form, where our effective length is basically the middle portion of it, right? This is my effective length, so that is actually 0.5 of the total length of the column, which in this case is what? 4 plus 4, so 8 meters. So 0.5 times 8, which tells me that its effective length is equals to 4, this length in the middle right here. So I can find the critical load about the x-axis. So I'm going to call it PCRX. So PCRX would then be pi squared, what was the Euler formula? Pi squared E I. Now what would I be? Is buckling about the x-axis, so it's I x, okay, divided by the effective length, which in this case is 0.5 times 8, so it is 4 squared. Okay, so Ix I take from here and E I take from the material properties given in the question. Great. So if I pop these values in my calculator, I find that my critical load about the x-axis turns out to actually be 1653 kilonewtons approximately. Okay, so that's the case for buckling about the x-axis. Great. Okay, again, please be careful using your right hand grip rule. If you point your thumb along the x-axis, then you can see in which your fingers curling tells you the direction in which it will bend and buckle. So it was about this direction. So it's buckling in something like this, as I already said to you. Okay, now let's think about the y-axis. Okay. So for buckling about the y-axis, again using my right hand grip rule, let me point my thumb in the direction of the y-axis. Then it's telling me what direction my bending would be occurring for this buckling about the y-axis. So my fingers curl something like so. So I am saying basically that I'm looking at bending in this direction. Okay, so I haven't yet drawn out the correct bent configuration or the buckle configuration, but I'm just showing you the plane in which it's deforming. So very carefully, if it's buckling about the y-axis, then clearly it's buckling in this plane which contains the x-axis. So this is the one for the buckling about the y-axis. Okay, great. So let's draw that one out. Now for this case, so about the buckling about y-axis, we've been told that the load carrying capacity has been increased by bracing it such that we now have a pin connected at its mid height. So there is actually a pin joint right here when we're analyzing buckling about the y-axis. So this time I'm looking at my y-axis in the plane. Okay, so y-axis is in the plane, it's going in. Okay, please, this is I've drawn a circle with a cross to show that my x-axis is going into the page, and then I'm going to draw out what my boundary conditions are. So in this case I'll just leave that on the side here. In this case I'm looking at the top right here. I have a fixed support right here, right? And then I have a pin in the middle. So I have a pin somewhere, pin joint here, and then again a fixed base like so. So this is basically acting like two separate columns that we know how to analyze, which is a fixed pin column at the top and a fixed pin column at the base. So what is the effective length for a fixed pin column? We know that takes a buckled shape something like so, where the effective length is basically 0.7 times the length of the column. Now what is the length of this column? That's actually just from the midpoint to the top. So it's actually this one. It's not the full length of the column. So it's 0.7 of the length of this column, which is 4 meters. So this time around, my critical load about the y-axis, for buckling about the y-axis, would then be pi squared e I y this time, because it's buckling about the y-axis, divided by the effective length, which here is 4 times 0.7, so 2.8 squared. If I pop the values in, I find that this is actually equal to approximately 461 kilonewtons. Okay. Now we've basically done the analysis separately for the x-axis and for the y-axis to find what our critical loads are for buckling about each of these axes. Now let me just be clear again about this thing, that I probably shouldn't have written this out right here. What am I looking for? Looking for this. So I'm basically saying this is buckling about the x-axis, that is not the x-axis, and this is buckling about the y-axis. Okay, these lines were not the axes. That's what I'm trying to be clear about. Okay, so buckling about the x-axis, buckling about the y-axis. Great. Okay. Okay, so now let's consider each of these. So we have our critical load y, which is clearly less than the critical load about the x-axis. So 461 kilonewtons compared to 1600 kilonewtons. So clearly then it's the lower critical load that dominates, because we will reach it first and hence that will lead to buckling. So therefore it's PCR about the y-axis which dominates buckling and is the actual critical load. So this is our critical load for buckling for this given column, right? And hence it's buckling about the y-axis that we need to be concerned about. Now let's also consider that once we reach this critical load, will the material have failed by then or not? So in order to do that, we of course need to find our critical stress. So we need to find sigma critical. Now that we find by just taking our PCR, which is the one about the y-axis, and dividing it by the cross-sectional area. So we see the cross-sectional area is given to us right here, so we can use that. And when we calculate it, the stress in the beam turns out to be, the longitudinal stress in the beam turns out to be 150 megapascals approximately. Okay, so this is the stress in the beam when it buckles, and now this one is clearly less than the yield stress that we are given. The yield stress is 410 megapascals. So that means that the material will not have failed and the structure will fail because of buckling and not because of yielding. Okay, that is, buckling is the failure mechanism that dominates. Okay, so our Euler analysis is applicable, first of all, because the material is still in the elastic regime. Euler is applicable, and buckling is our dominant failure mechanism. So buckling dominates. Right. Okay. So just one more example to make this concept of buckling about the different axes being completely clear and looking at different types of supports. So let's look at example number 3 now. So example 3. Now again, we have a column This time around it's aluminium, which is fixed at its base and it's braced at the top by a cable, this one shown right here, so as to prevent movement at the top along the x-axis. Okay, so only along the x-axis. Okay, so that means it's unable to move about this direction. Okay, so we'll see what that means. If it is assumed to be fixed at its base, determine the largest allowable load P that can be applied. Use a factor of safety for buckling to be 3. And then taking the material properties, the yield strength, and so on and so forth. Okay, so let's have a think about this. So basically we are saying that it can't move in this direction. It can't move in that direction. Okay, so what does that mean about buckling in about which of the axes? Okay, so what we'll do is we'll basically go back very simply again to start considering buckling about each of the axes separately. So let's first start with our x-axis and now have a think. So again, if you're looking at the x-axis, thumb pointing in the direction of the x-axis, our fingers curled telling us what is the direction of the buckling. So it is this plane, the one that we're looking at for the x-axis. It's this plane in which buckling occurs. Okay, now have we been told anything about, sorry, I'm looking at the x-axis, about whether deformation has been constrained here? Because that's where it's moving for this axis, right? This is the plane of buckling. No, nothing. It's only constrained in this direction, so it's free to move here. It's free to move and bend in this direction. That is, if we're looking at buckling about the x-axis, so buckling about the x-axis, should probably also write here buckling about. Okay, buckling about. Okay, because I'm not pointing out an actual x-axis here, we're looking at it, it's in the plane. So buckling about the x-axis, we are saying that we have just a fixed base at the fixed support at the base, whereas at the top here, nothing, we aren't told anything in the question. So it's free to deflect and bend and go wherever it wants. So it's basically a free support. So it's this problem that we are familiar with. Now in this case around, we know that our effective length is basically L effective is twice the length of the column, and the length of the column is what? It's 5 meters. So here our effective length is then 10 meters. So finding that out, I then can find my critical load about the x-axis. Again, pi squared EIX, very important, buckling about the x-axis, hence IX, divided by effective length squared, 10 squared. Don't forget the squared. Now that gives me a value of 424 kilonewtons if I substitute in all the values from the question. Now let's consider buckling about the y-axis. Now that's the one where we have an issue. So for the y-axis, using our right hand grip rule, we see that buckling is the one occurring in this plane for the y-axis. And now that's exactly where we've been told that at this point it is unable to move in this direction, because there is no movement along the x-axis. So here it's acting like a pin joint basically, right? Because it's only constraining movement. Okay, so it can't deflect here. Nothing is being told about its the rotation. So it's not a fix, it's just a pin about the y-axis. So here, so if I'm looking at buckling about the y-axis, I get a pin joint at the top and a fixed base here. So that basically I know looks like this. Now here I know the effective length is, what is L effective? .7 times the total length of the column, which is of course still 5. So 0.7 times 5, which is 3.5. So my critical load about the y-axis is equals to, as before, pi squared EI. By now you would have, I've said it so many times, you would have memorized the formula. So pi squared EI y divided by L effective squared, which in this case is 3.5 squared. If I calculate it, that turns out to be 1.31 meganewtons. Okay, so looking at these two critical loads about the x and the y-axis, we can see clearly that it's the critical load about the x-axis that has the smaller value, and hence that's the one that will dominate failure. Okay, but let's not forget that we actually also have to use a factor of safety for buckling, the value of 3. Okay, so how do we include this? Okay, right. For this, we must remember basically that buckling occurs once our smallest critical load is reached, right? So if we want to introduce a factor of safety into that, we basically need to make sure that we are well below that critical load. So in this case, for example, if I draw that out, if we are saying that our real buckling load is this PCR X, and once this reaches, we will reach failure, and we want to introduce a factor of safety of 3, then that basically means that we need to keep our allowable load, or the load that we have in our actual system, to be that much less than this critical load, so that we don't even approach it. Okay, so I'm saying that my P allowable basically is actually, let's call it P allow, is actually this critical load divided by the factor of safety, right? So that's 424 divided by 3. So what does that turn out to be? Something 140 kilonewton or something. Okay, so the reason why I'm bringing this up 140 kilonewton is so that we can see clearly. Basically, we are saying that even though when we calculated analytically, the critical load for the structure was actually 424 kilonewton, we will only allow our structure to be loaded up to 140 kilonewton, so that we have a factor of safety of 3, making sure that our system is well under buckling. Okay, so that's how the allowable load is calculated for buckling. Okay, so please be careful about this, introducing the factor of safety on a buckling load. Okay, great. So this is basically our allowable critical load for our system. Now next, we also are given the yield strength, so it's a good idea to actually check whether our material fails or yields or it buckles. Does it fail by yielding or by buckling? So in order to do that, it's probably a good idea to calculate our sigma critical. Now what I'm going to do is actually find sigma critical without the factor of safety. Okay, so let's just see what that gives us. So if I use then our 424 divided by what's happening, 424 kilonewtons divided by the area, I get something like 56 megapascals. Okay, now the reason why I've chosen to go for my critical load even without the factor of safety is because it already turns out to be such a small value. So the stress sigma critical turns out to be 56 megapascal. That's so far below the yield strength, 215 megapascal, that even if I had no factor of safety, the system would still be failing by buckling and not by yielding. Okay, so that basically means that my dominant failure mechanism is actually buckling, not yielding. It will buckle. Okay, because sigma critical is less than sigma y, less than sigma y. Okay, so this, let me repeat this, that I have not included the factor of safety in sigma critical's calculation, just because even with one, so no factor of safety, that means one, right? The system is still buckling, so I just don't even need to consider my lower sigma critical. Okay, so that's basically it for our buckling examples. If you have any questions regarding this, we will discuss them during our Q&A on Thursday. Okay, Allah Hafiz.